Hey everybody in Calc BC. Today we're going to be starting lesson 2.4, which is our applications of derivatives lesson part 2. In this lesson, we're going to be looking at particle motion, optimization, and approximation. And as I've been saying all unit, this is just going to give us some key information about specific pieces of differentiation from Calc AB. It's not, it's an overview. It's not hitting every single topic, and we're going to go back throughout the year and hit some more topics that we're skipping over here, but this will give us a good foundation. If you look at the screen right now, you'll see that in College Board's course description, this is coming from their Unit 4 and Unit 5 from the AB and BC combined outline. So in Unit 4, these two lessons right here are our particle motion lessons. Then in 4.6 is approximation. And then at the end of Unit 5, they have their lessons on optimization. So that's what we're going to be focusing on today. Feel free to check out the exam description if you want information from College Board, but I'm going to pause right here and go ahead and get out the notes. All right, so here are the notes. Again, today we're focusing on particle motion, optimization, and approximation. We're going to start out with particle motion. So example 1, a particle moves along a horizontal line so that its position at any time t is greater than or equal to 0 is given by this function, where s is measured in meters and t is in seconds. Find the velocity at time t and at t equals 1 second. So first of all, just making sure that we understand this, we have a particle moving along a horizontal line. So if we wanted to make a quick sketch, basically we have a number line here, there's a 0, and this is our position function. So whatever this value is, when we plug in a time in seconds, it's going to tell us in meters how far we are to the left or to the right of this 0 on this horizontal line. Velocity, if the velocity is positive, it's moving to the right, and if it's negative, it's moving to the left, because that's how we would think of a number line, right? The positive numbers are to the right, the negative numbers are to the left. If we're moving forwards, it's considered to the right. So that would be a positive velocity. And we know how to find the velocity equation, right? Because if we have the position, velocity is just the derivative of the position. So velocity, we could say, is s prime, which we can find using the power rule. So we have 6t squared minus 14t plus 4. Okay, so that is actually the first answer. Find the velocity at time t. So there we go. And now we're going to find the velocity at t equals 1 second. So now all that means is that we plug in 1 for t. So we have 6 times 1 squared minus 14 times 1 plus 4, which is going to be 6 minus 14 plus 4, or negative 4. And the position was in meters, so this velocity is going to be meters per second. And again, that's negative, so it means we're moving to the left, negative 4 meters. So we're going to move 4 units along this number line every second at that exact moment. Letter B, when is the particle at rest? Moving right, justify your answers. So first off, if we're at rest, it means that the velocity is 0, right? If you're not moving, you don't have any speed or velocity. So we can set that velocity function equal to 0 and try to solve for t. Because we want to know when. So we want to know what t's or what time is this particle at rest. I feel like this isn't completely focused. All right, let's try this. So we have, first of all, each of these numbers is even, so I'm going to divide out 2. And then I'm going to try to factor. I end up with 3t minus 1 and t minus 2. And I set each one of those factors equal to 0. And I add 1, divide by 3, I get t is 1/3. And on this side, I'll get t is 2. And these are both in seconds. And that's when we're at rest. So we're at rest at 1/3 seconds and at 2 seconds. Then we want to know when are we moving right. So to find that out, we want to know when the velocity is positive, right? If the velocity is positive, we're moving to the right. So we're going to make a sign chart for velocity using these zeros, which are acting like our critical numbers here. So we're going to have a point or a tick at 1/3 and at 2. I'm going to try plugging in different values here. Well, it's also important to realize that we don't care about any times that are negative. It says time is greater than or equal to 0 at the beginning. So the left end of my number line can actually be 0, not an arrow. So if we plug in a number between 0 and 1/3, maybe 1/6 or 0.1, you plug that into the velocity, and you're going to get a positive answer. Plug in a number between 1/3 and 2, so maybe you plug in 1 for t, you're going to get a negative answer. Plug in a number greater than 2, so maybe you plug in 3 for t, you're going to get a positive answer. So that's what our sign chart looks like. And so we want to know, when are we moving to the right? Give me 1 second. All right, let's try this again. So this is moving to the right anytime that the velocity was positive. So that's going to be from 0 to 1/3, union with the interval from 2 to infinity. And again, we start at 0 because at the beginning we were told that t is greater than or equal to 0. Letter C, find the acceleration at time t and at t equals 1 second. So now we know that acceleration is the second derivative of the position function. So we're going to take that same function from above, and now we're going to take the second derivative. So it's going to be 12t minus 14, and everything else is getting dropped off. So there we go. There's our first part. And when t is 1, we're going to plug in 1 for the acceleration function. And so we end up with 12 minus 14, which is -2. And this acceleration, since we were in meters per second, now it's going to be meters per second squared. And acceleration, since it's the second derivative, it's going to tell us if we're how we're accelerating, right? So it tells us if we're speeding up or slowing down. We'll get more into that as we go. But if the signs are the same, which they are here at 1, right? So if the velocity was negative and the acceleration is negative, it means we're already moving left, and we're moving more and left faster and faster because acceleration is also negative. So we're going to be speeding up. But anyway, we found the answer to part C. Letter D, find the displacement of the particle between t equals 0 and t equals 1.7 seconds. Explain the meaning of your answer. And this goes hand in hand with letter E. So we're going to talk about displacement versus distance traveled between 0 and 1.7. So let's start with displacement. Displacement just means what's the position at 0, what's the position at 1.7, and what's the difference between those two positions. That's the displacement. That's like from point A to point B, how much distance is between those 2 points. That's the displacement, right? That's how much it was displaced from the original. So if we plug in 0 for the original position function, which is way back up in the given question, everything's going to cancel out except for the 5. And this is in meters. And if I plug in 1.7, I'll do that really quickly here. We're going to get 1.396 if we multiply that all out. And so what we do to find the displacement is we start with the original and we subtract the new position. Sorry, I guess I did that the other way around. We start with the new position and we subtract the original, and we're going to end up with negative 3.604 meters. So our displacement is telling us that the particle is now Well, now being at 1.7 seconds. Negative 3.604 meters from where it started. So at 1.7 seconds, we're negative 3.604 meters from where the particle started. However, that is not always the same as the distance traveled, right? Think about if we have a particle here on our number line. What if we start here and we move this way and then we come back? So we went over here and then we went into reverse and ended up here. All right. The displacement after all of that happens would just be the distance between these 2 points, because this is where we started, this is where we ended. But maybe we traveled further than that and then came back. If the question asks for distance traveled, it wants to know the entire length of the journey, not just where you ended, right? And this would matter, for example, if we were talking about like a car and how much gas you used. Well, the gas that you use doesn't care just where you started and where you ended, right? Like when I drive to school and then I drive home, because I ended where I started, it doesn't mean that I didn't use any gas, right? The gas doesn't care if we ended where we started. The gas cares how far we traveled. So to figure this out, we need to first think about where is the velocity zero, because that's where it might change direction. And we specifically care between 0 and 1.7. So if we look back up, we already set the velocity equal to 0. And we found it's at 1/3 and at 2. Since our interval's from 0 to 1.7, we only care about the 1/3. Because 2 is outside of our interval. So that's going to not impact this. So our total distance is going to look like this. It's going to be the absolute value of the position at 1/3 minus the position at time 0, plus the absolute value of the position at 1.7 minus the position at 1/3. So basically we're taking the absolute value of the distance for the first interval plus the absolute value of the distance for the second interval. And the reason that we're using absolute value is because we always want it to be positive. And the reason we're splitting it here is because this at 1/3 is where it might change direction. So we're going to split it in 2 just in case it changed direction there, so that we can make sure we count every portion of going to the right or going to the left as a different length. So let's figure this out. If we plug these numbers in, which I've already done, we're going to get 152 over 27 minus 5 plus 1.396 minus 152 over 27. And we're going to start to reduce that. I ended up with some crazy fractions here. In the end, I had 32,827 over 6,750, which is not very helpful in this context. So I'm going to write that as a rounded decimal. I get 4.863 meters. So you can tell between D and E here that our answers were definitely different. The displacement was negative 3.604, but we actually traveled more than that because it must have gone past and then come back when it changed direction. All right, so hopefully that makes sense. We are going to keep going. Ooh, there's one more part, letter F. Letter F, when is the particle speeding up? Justify your answer. Okay, so we're kind of just talking about this, but let's go into some more depth here. Hint, since speed is the absolute value of the velocity, the particle is 1, speeding up when the velocity and acceleration have the same sign, either both positive or both negative, and it's 2, slowing down when the velocity and acceleration have opposite signs, 1 is positive and 1 is negative. So first of all, remember that speed is the absolute value of the velocity. Speed doesn't care which direction you're moving, right? Like in your car, or if you're in a car and you switch into reverse, right, suddenly your speed doesn't read as a negative number, right? The speed is still positive even though you're driving backwards. That is real life, that's true. So even though the velocity might be negative at this part of this graph, the speed is the absolute value. So you would see it bounced up above the x-axis like this. So to answer part F, we're going to draw a double sign chart showing both the signs of the velocity and the signs of the acceleration. So what we're going to do here is we want to know, when is the velocity equal to 0? When is the acceleration equal to 0? And we're going to then create this sign chart comparing all of the values. And remember, just like before, we're going to start at 0 no matter what, and this way is going to keep going to infinity. We already did this first part, right? We figured out when the velocity was 0. This is the same question as the previous page. And we figured out that t was 1/3 and t was 2. If we wanted to know when the acceleration is 0, right, that might be where we find an inflection point if we were looking at the graphs on an xy axis. 12t minus 14 equals 0. If we solve that for t, we would add 14 and divide by 12, we would end up with 7/6. So we're going to put all of these points on our sign chart here between 0 and our arrow to infinity. So 1/3 is the smallest. And then 7/6 would be next. And then 2 is the largest. And then it would keep going. So between 0 and 1/3, from the previous page, we already figured out that the velocity was positive there. And we also figured out that between 1/3 and 2, the velocity was negative. And then greater than 2, the velocity was positive. Now we have to do the same thing for the acceleration. So the acceleration is only going to change below 7/6 or above 7/6, because that's when the acceleration was 0. So if we plug in a number smaller than 7/6, maybe 1 in here, we would end up with 12 minus 14. So it's going to be negative. So anything smaller than 7/6 is going to be negative. If we plug in something larger than 7/6, like maybe 2, we're going to get 12 times 2 is 24 minus 14, and that's positive. So everything above 7/6 is positive. You can plug in a specific number between every interval if you want, and you'll find the same thing. So now we want to know, when is this speeding up? So again, speeding up means that the velocity and the acceleration are the same sign. And we're going to say the particle is speeding up over the intervals 1/3 to 7/6, and from 2 to infinity. So from between 1/3 and 7/6, it's speeding up to the left, and from 2 to infinity, it's speeding up to the right. But the question didn't ask that. I just want to know, when is it speeding up? And that's what we wrote. So that's our answer. All right, so that's a brief overview of particle motion. We're going to move into optimization. A particle moves along the x-axis, so its position is given here from 0 to 4. Find the minimum velocity of the particle and the time at which it occurs. Justify your answer. So there's a couple methods that we're going to look at, 2 methods specifically. The first method is the candidates test, where we're going to find all of the potential candidates and then test all of them. So we're going to find v of t and v prime of t, because remember, we're looking for the minimum velocity. So for optimization questions, whatever you're trying to minimize, you're always going to go one derivative further than that. So if this is our position and we're finding minimum velocity, first we have to find the velocity. And it's going to be 3t squared minus 10t plus 12. And then we're going to find the derivative of the velocity, right? To minimize something, you find the derivative of that first. And that'll be 6t minus 10. Okay, so we want to set that equal to 0 to find the critical numbers, right? So this is really like the second derivative, so we don't normally think about that as critical numbers, right? But remember, we're kind of orienting everything around the velocity here. So this is now our version of the derivative function. So this is going to give us our critical numbers. So we're going to have 0 equals 6t minus 10. So we have 10 over 6, which is 5/3, is going to be t. And then we're going to make a chart. So it's our t and our velocity. And we include the endpoints and our critical number. So the endpoints were 0 and 4, and 5/3 is between 0 and 4. So we are definitely going to include it. And we're going to find the velocity every time, like we did when we found absolute max and absolute min values. So if we plug in 0 to the velocity function, we're going to end up with 12. If we plug in 5/3, we get 11/3. And if we plug in 4, we get 20. So if we want to know the minimum velocity, we look at which of these values is the smallest, and it's going to be 11/3. So we have a minimum velocity of 11/3 at t equals 5/3. All right, so that's our first look at optimization. We minimized the velocity, right? Let's keep going. We're going to do a second method of the same question. First, we're going to find v of t and v prime of t. It said v prime of t equal to 0 to find the critical value, so that's what we already have done. So if you see the previous page, then you will see that our t is 5/3. And we already did that. All right, C, first method. And then we're going to draw a sign chart and find the values of t where v of t is a minimum that way. Okay, so if we draw our sign chart, we only have one critical value at 5/3. And our endpoints are 0 and 4. So if we plug in a number like 1 into our velocity function, which, just to remind you, was 3t squared minus 10t plus 12. We're going to end up with 3 minus 10 plus 12, which is definitely going to be oh my goodness, just kidding, right? The sign chart is specifically looking at the v prime. I was going to say, that's not what I thought it was. So our v prime was 6t minus 10. Because we're going to be trying to figure out if our sign switches from negative to positive, because remember, that'll tell us the slope of the velocity. So if we switch from negative to positive, that's giving us a minimum. So if we think about this, okay, here we go. So we plug in 1, we get 6 minus 10, that's negative. We plug in 2, we get 12 minus 10, that's positive. Okay, there we go. And so we made our sign chart, and the sign only switches from negative to positive once, which means we have a minimum at t equals 5/3. All right. But there is a special note here. If the absolute maximum or absolute minimum occurs at an endpoint and not a critical number, you must use the candidate's test to find your answer. So most of the time we're going to be wanting to use the first method, because this only works in a very specific situation. Since this velocity function was a quadratic, we knew it would only switch signs once. So we got lucky here. But if this was plus minus, and this we knew was a maximum, we wouldn't know which endpoint might be the lower minimum to find the absolute minimum. So then we would have to check each one. Honestly, it's not going to save you that much time. You might as well just always use the first method. But this does work sometimes to save you a couple minutes, potentially, to find the minimum, to optimize, right? But let's try some application questions. So let's take a look at this example. A swimmer is 2 miles in the ocean. So here's our swimmer down here. How do you draw a swimmer? I don't know. There, we're doing freestyle, right? Yeah, so there's our swimmer. Here's some water. Okay, and wishes to get to a town 3 miles down the coast, which is very rocky. So here's the shore. This is the shore up here. The swimmer needs to swim to the shore and then walk along the shore. He can swim 2 miles per hour and walk at 4 miles per hour. To what point should he swim along the shoreline so that the time it takes to get to town is a minimum? All right, so the question is, to what point should he swim along the shoreline? So we're asking, what is this length right here? How far along the shoreline should he be by the time he gets to shore from swimming before he starts walking so that it takes him the least amount of time to get to the town? All right, so this type of question probably looks familiar from AB. I like to define my variable with whatever the question's asking me at the end. We want to figure out what point he should swim to along the shoreline. So I'm just going to call that X because that's going to be our final answer. And then I'm definitely going to need something to represent this distance and something to represent this distance. So this is going to be our 3 miles minus X. And this length, since this is a right angle, we can use Pythagorean theorem. And if we have x squared plus 2 squared, so we have x squared plus 4, and then this becomes the square root of that, right? I can write that out if you want. You'd see we have x squared plus 2 squared has to equal c squared, so x squared plus 4 has to equal c squared, and then we square root, and we know it's going to be positive. We don't have to write plus or minus. So we have c is square root of x squared plus 4. Okay. And how are we going to minimize this? So first of all, we could say that the distance that this person travels is going to be the square root of x squared plus 4 plus the 3 minus x. All right, so he's swimming this far, walking this far, but that's not really going to help us that much right now because we don't really care about minimizing the distance. We care about minimizing the time. So we really need to know how long is this going to take this guy? And so what we need to think about is if he's swimming 2 miles per hour and he's traveling this far, how do we figure out how long that's taking? So think about if you're going to swim 6 miles and you can go 2 miles per hour. First of all, more power to you because that's awesome. I don't think I could swim 6 miles. I definitely couldn't swim 6 miles straight. But if you're swimming 6 miles and you're swimming at 2 miles per hour, you're going to do 6 divided by 2 to get, that is going to take 3 hours, right? Another way to think about it is if we could do the miles that you're swimming divided by the miles per hour. And if you kind of switch around our units, you can think about multiplying by the reciprocal of the denominator, right? We have miles over miles per hour as miles times hour over mile, and the miles cancel out, so we're left with time. Okay, so hopefully that you can see now that what we're doing here is we're going to take the distance and divide by our speed to get the time. So we're going to take that's x square root of x squared plus 4 divided by how fast we can swim, which is 2 miles per hour. And we're going to take the 3 minus x and divide by how fast we can walk, which is 4 miles per hour. So we have our time, right? The part that we swim, we divide by 2. The part that we walk, we divide by 4. And what we want to do is minimize that time. So we're going to take time prime or the derivative of time, right? Because if we're going to try to minimize something or optimize something, we always want to take the derivative of the function that we're trying to minimize. Okay, so for this first one, I'm going to think of it as 1/2 instead of that. And so it's going to be 1/2 times the square root of x squared plus 4. So we have 1/2 times, this is raised to the 1/2 power. So it's going to be times 1/2 x squared plus 4 to the negative 1/2 times the derivative of the inside, which is 2x. And for this part, this is really, I would think of it as 3/4 minus 1/4 x. So if we take the derivative of that, 3/4 goes away, and this just becomes minus 1/4. Right, so for this first part, we have a chain rule. So it's 1/2 was already on the outside. We multiply by 1/2, so that's the power of this, right? You can think of this as x squared plus 4 to the 1/2. So we pull out the 1/2, change the exponent, subtract 1 to make it negative 1/2. We multiply by 2x for the chain, right? That's the derivative of the inside. And then we get minus 1/4 at the end. Okay, so we're going to set that equal to 0. So we have 0 equals, and I'm going to try to rewrite this so that it doesn't look so crazy. So this 1/2 can cancel with this 2. The x is on top. There's a 2 left over on the bottom with this square root because it has a negative power. So it's going to be square root of x squared plus 4 down here. Still minus 1/4. And I'm trying to minimize this. So let's see what we can do here. I'm trying to solve for x. So I'm going to add 1/4. Then I'm going to multiply by that denominator. And I end up with 2 times 1/4, which is going to be 2/4, which, yeah, 1/2. Square root of x squared plus 4 equals x. So I just took this whole denominator and multiplied it to the other side. I'm going to take that 1/2 and multiply it back over here because I want to get the square root by itself so I can square both sides. So I have x squared plus 4 equals 2x. I'm going to square both sides. And I end up with x squared plus 4 equals 4x squared. And I can subtract the x squared. And I'm going to move up here. And I can divide by 3. So I got 4/3 equals x squared. And then I square root. So I end up with plus or minus the square root of 4/3 equals x. And so we know based on our sketch that x is definitely going to be positive because it's a distance, it's a length. And a length is always positive. It wouldn't make any sense if the swimmer swam this way first and then walked to the town. There's no way that's a minimum. So our x is going to be positive. So our x is going to be the square root of 4/3, which is approximately 1.155, and this is in miles. So that's how long this length is. That's the point to which he should swim along the shoreline so that the time it takes to get to the town is a minimum. Now, we weren't asked to find this distance and this distance. We could find that distance, but all we needed was x, and we got it. So there you go. Perfect. Let's keep going. All right. Closed box with a square base is to be built so that its volume is 72 centimeters cubed. If the bottom of the box costs 60 cents per centimeter squared, the sides cost 35 cents per centimeter squared, and the top costs 30 cents per centimeter squared, find the dimensions and the cost of the least expensive box. All right, so we know right off the bat, this is definitely an optimization question. So I'm gonna sketch this box real quick. Looks something like this. And of course, there's like the sides that we can't see. And we know this is a square base. So I'm just going to decide that instead of doing length, width, and height, I'm going to do width and width, or W and W. And that's going to represent that the base is a square. So the length and the width are equal, so I'm just going to do 2 W's. And then the height is not necessarily the same. We just know it has a square base. So I'm going to keep a separate variable for height. And we want to know the dimensions and the cost of the least expensive box. So the cost will be what? We know it is, well, it's 60 cents for the bottom. So 60 cents per centimeter squared. So if we think about the area of the base, it's going to be W times W, right? Think of that as a square. So we have W times W, and that's going to be giving us the square centimeters of the base. So our cost is going to be 0.35 times W times W. So that's the, oh my goodness, I wrote that wrong, didn't I? I just wrote what I saw. The base is 60 cents. So I'm going to cross that out, 0.60 times W squared. That's for the base. For the sides, first of all, we have to think about that there's 4 sides of our box. So we're going to multiply whatever we get by 4. The sides cost 0.35. And to get their dimensions, it's going to be the W times the H. So each side is W times H. You can kind of go around our shape and see that. It's going to be W times H. And then the top is going to be 30 cents times, again, the W squared, because the top is still the W times W. So we have 60 cents times W squared plus 4 times 35 cents times W times H plus 30 cents times W squared. Okay, so before I go any further, I just want to make this a little bit prettier. And we have 0.6 squared, so, sorry, 0.6 W squared plus 0.3 W squared. So we're going to end up with 0.9 W squared, 4 times 0.35. Let me multiply that out real quick. 4 times 0.35 is going to be 1.4 WH. Okay. So then we still have 2 variables, and I don't want to, we do know that to minimize the cost, we're going to take the derivative of this. But I don't really want to do that yet until we only have 1 variable. It's kind of like related rates almost here. I guess it is related rates. Because we also know something that we didn't even use yet from the question. We know that its volume is going to be 72 centimeters cubed. So over here, I'm going to write that out. The volume of this box is going to be the length times the width times the height. And the length and the width are the same. So I'm doing W times H. And we know the volume. Volume is 72. So it's going to be 72 equals W squared H. Okay. So what I'm going to do here is solve this for H, because that's going to give us the simplest answer here. If I solve for W, I'm going to have to square root. So I'm going to do 72 over W squared equals H. And I'm going to come back over here and plug that in so that we don't have to worry about H anymore. So now this equals 0.9 W squared plus 1.4 times 72 over W squared. And you know what? There should have been a W before that. So it's 1.4 W and then this H, 72 over W squared. I'm going to simplify that. So we get 0.9 W squared plus, what's 1.4 times 72? We get 100.8. And that's W over W squared. So it's going to be W to the negative 1. And now we only have 1 variable. So now it'll be much easier to take the derivative. So I'm just going to abbreviate this as C prime. It's going to be 0.9 times 2, so 1.8 W. 2 minus 1 is 1, so our power is 1 there. And this will be minus 100.8 W to the negative 2. And in order to figure this out, we are going to set this equal to 0, because think about that the original had an exponent of 2, so it should give us, when we have a 0, it should give us the minimum here. So we're going to have 0 equals 1.8w minus 100.8w to the negative 2. And let's see, how are we going to solve this? I would say, let's move this to the other side. So first of all, I'm going to think of this as over w squared instead of w to the negative 2. I'm going to move it to the other side. We get 100.8 over w squared equals 1.8w. And I'm going to think of that as over 1 so that now I can cross multiply, or really just multiply the w squared to the other side. So I get 100.8 equals 1.8w cubed. And so then I divide by 1.8 and I get w cubed equals 56. So w is going to be the cube root of 56 after all of that, which is about 3.826 centimeters. Okay, so we got the w. The question wants us to find all of the dimensions and the cost. So we've got the w, we can find the h by plugging in w here. So if we do 72 over 3.826 squared, we're going to end up with the h, which is about 4.919 centimeters. So there's our dimensions. And then last thing, we have to find the cost. So our cost formula is up here. I'm not going to write it all out, but if you plug in this w and this h, what we're going to end up with is about $39.52. Okay. So that was our box question, all right? Hopefully that makes sense. Take a look back over it if you need to. Everything should be kind of worked out and organized here, but let me know if you have questions. Next up, we're going to talk about linear approximations and differentials. So the tangent line to a curve gives us a useful way to approximate a value on the curve. We usually write our tangent line equations in point-slope form, or for a particular value of x1 named a, we could write it like this. Yeah, pretty straightforward. I think we usually see point-slope form like this. But it's the same thing down here because the x1 was just changed to a and the y1 was just changed to f of a. And that showed us that f prime of a is really what the slope means, but it's the same idea. When we are using a tangent line to find an approximation of a value on the curve, we might want to rearrange the terms of the tangent line equation to write it like this. This is the same thing, but we just added f of a to the other side, right? Y represents the y coordinate of a on the tangent line. This gives us an approximation of f of a. The y coordinate of a on the function f of x is represented by f of a. F of a is the actual value. Okay, so what are we talking about here? Well, basically, this is going to give us a linear approximation, which means, let's say we have an x and a y axis here, and our curve looks like this. And maybe that curve has a really complicated equation that we don't know. But we know that there's some tangent line right here. So maybe at this point, we know the value of the x and the y value, we know the ordered pair, and we know the slope of the tangent line. Well, maybe over here, we want to know, what is this point? And maybe we don't have the curve, so we don't know what that point is, but we can use the tangent line to approximate. The value on the curve. And you can already tell it's a little bit off, and the further away we get, the more off it's going to get. Like if we tried over here, we'd have our approximation down here, and the curve would actually be all the way up here. But here it's pretty close. So that's what we're going to try to do here. So let's take a look at this example. Given f of x equals x squared, a, write the equation of the tangent line to f at x equals 1. So first of all, we are going to need to know the ordered pair at x equals 1. So the f of 1 is 1 squared, which is 1. So we know, first of all, that we have our ordered pair at 1, 1. right? Then we want to know the derivative so that we can find the tangent line, right? Because we need the slope. So f prime of x equals 2x based off of the original equation. So f prime of 1 is going to be 2 times 1, or 2. Okay, so now we have the point and we have the slope. So if we go back to our point slope form, it was y minus y1 equals m times x minus x1. And so we're going to have y minus 1 equals 2 times x minus 1. All right, so there's the equation of the tangent line. Depending on how you do it, it might look a little bit different. We could kind of distribute the 2 and then add the 1 and end up with 2x minus 1. Either way, it doesn't matter. Either of those answers is fine. We're going to move on to letter B. Use your answer for A to approximate f of 1.01. So f of 1.01, we're going to say is approximately, and we're going to take our tangent line and plug in 1.01. So it's going to be 2 times 1.01 minus 1. And we're going to end up with 1.02. That's our approximation. So think about if this was our curve, we just found this point. We found this y value, which is probably pretty close to the real answer, because 1.01 is pretty close to 1, but it might not be the exact answer. So in letter C, we're going to find the actual value. So we're going to go back to the original equation, x squared, and plug in 1.01. So the actual, so now I'm using a real equal sign here. The actual value of 1.01 was 1.01 squared, right? Because we go to the original equation and plug in 1.01, and we get 1.0201. So this was our approximation. This is where we really are. D is the amount of error. So we want to know what was the difference between our approximation and the real answer. How much error did we have? So we're going to subtract them. And this was a pretty good approximation because the error is 0.0001. All right, so that's an intro to linear approximation. We're going to do one more example there. Use a tangent line approximation to approximate the value of the cube root of 127. To do this, let f of x equals the cube root of x, and then choose a perfect cube close to 127 and build your tangent line at that x value. So we don't know the cube root of 127. And maybe this could be a question where we don't have access to a calculator. So what we can do instead is think about, well, what numbers close to 127 have a perfect cube root? That's a whole number. The answer to that is 125. The cube root of 125 is 5. 5 times 5 times 5 is 125. So that's going to be pretty close to the cube root of 127. So we're going to let x equal 125 for our question. So, and f of x is going to be the cube root of x. So if we try to find f of 125, it's going to be the cube root of 125, which is 5. So that means we have an ordered pair of 125, comma 5. And we're trying to use tangent line approximation. So we need to find the slope, right? We're doing the same process we just did in the last example. And so our f prime of x, if our initial equation was x to the 1/3, our f prime is going to be 1/3 x to the negative 2/3. So our f prime of 125 is going to be 1/3 times 125 to the negative 2/3. And that actually equals 1/75 once you kind of multiply that out, right? You can kind of think of this as being in the denominator, and we cube root the 125 and get the 5, and then square it, and we get 25 times 3, which gives us the 75. Okay, so then we have to find our tangent line. So it's y minus y1 equals m times x minus x1. We plug in our ordered pair and our slope. So we have y minus 5 equals 1/75 times x minus our x value, which was 125. And I'm going to actually solve this for y. So we end up with y equals 1 over 75x. By the time you add the 5, you get plus 10 thirds. So we did 1 over 75 times 125, and then we added 5. We get this. So that's our tangent line. And so then we find f of 127. Think about our original question. We're going to approximate this. So I'm using the curly equal sign. And I'm going to use this tangent line and plug in 127. And that equals 5.027. So that's our approximation for the cube root of 127. All right, that was the same process again as in the previous question. All right, last thing in this notes is just an intro to the idea of a differential. And we get an intro to kind of some of the history of this also. So first of all, Leibniz used the notation dy dx, dy over dx, to represent the derivative of y with respect to x. The notation looks like a quotient of real numbers, but it is really a limit of quotients in which both the numerator and the denominator go to 0 without actually equaling 0. Leibniz did most of his calculus using dy and dx as separate entities, but he never quite settled the issue of what they were. To him, they were just infinitesimals, which is non-zero numbers, but infinitely small. It is tricky to define dy and dx as separate entities, but since we really only need to define dy and dx as formal variables, we usually see them as dy over dx, and that must mean the derivative, right? We oftentimes will write dy over dx, and we even just say dy dx, and that means the derivative, right? But they can be considered differently, which is what we're going to do in these next couple questions. So in this example, find the differential dy given y equals 5x cubed. So we're going to think of dx as an independent variable, and dy is going to equal f prime of x dx. So in other words, instead of writing this as dy dx equals 15x squared, we're going to separate the dy and dx. So we're going to write dy equals 15x squared dx. So it's just like we're multiplying the dx to the other side. So that's not the answer we want. We want this answer. Okay. Let's look at it with some different variables here. The radius r of a circle increases from 10 meters to 10.1 meters. Use the differential dA to estimate the increase in the circle's area A. Excuse me. So we're going to start by writing down the area formula for a circle, and the area is pi r squared. And we're going to then find the differential dA. So dA equals, and we still find the derivative of the other side in terms of r, so it's going to be 2 pi r, right, because we're bringing 2 in front, and then subtract the exponent, subtract 1 from the exponent, and then we multiply that times dr. And the question is asking us to estimate the increase in the circle's area, A. And so to do that, we're going to have 2 pi times the original radius, 10. And then for dr, we're going to plug in the difference between the original radius and the increase, because think of dr as the change in r, right? So in this case, the change in r is 0.1. So to find the increase in the circle's area, we can plug in the increase in the radius here, and that will actually calculate that for us. So we have 2 times pi times 10 times 0.1, and we're estimating the increase in the circle's area to be 6.28318537, etc. I just wrote all that out. It didn't tell us to round it, so I'm just going to write all of the numbers that I have. And that's going to be important for the next question, because we are going to look for the difference between this value and the real deal. Let's compare the estimate that we found in A with the true change, delta A. So to figure that out, we're actually going to find what is the area if we plug in 10 for the radius. So we're going to have pi times 10 squared which is 314.159, etc. And if we plug in 10.1 now for the radius, we get 320.4738, etc. So the difference between the true areas here, if we subtract these two numbers, we're going to get 6.314601193. And if we compare that with our estimate, the error is the subtraction of the two, which is going to be 0.0314158857, etc. Now, depending on how you type all this into your calculator, and depending on what brand of calculator you have, it's going to change how it's multiplying by pi. So you might have slightly different numbers further along in these decimals. That's okay. As long as the first couple are the same as mine, then we are all set, okay? So I think that's probably the most confusing part of this, but that is the end of the notes. So we've seen a lot throughout these notes, and the practice problem set will hopefully cement your learning, or at least your memory of everything that you learned last year. And as always, let me know if you have questions. Thank you so much for watching.